So far, we've talked about confidence intervals and tests of significance for one variable. Now we're going to start talking about two variable, which is called inference about regression. So to begin with, we'll do a little review of what a distribution means for one variable. So here we have a collection of 25 children and their height. So this is just children height. It's one variable. Over here you can see the distribution of that one sample. And I have calculated the mean of that one sample is 142.139, which is right there. Right, so that's the one mean for that one sample. Now if we took a different sample, like this, then all of a sudden we have 144 as our mean, and that's that one right there. We can then collect more samples. You can see each sample is a little bit different. There's always distribution. Right? We can start collecting maybe 10 samples at a time, make this go a little faster. Maybe we can go 100 samples at a time. So now we're collecting lots and lots of samples, and you can see that pretty soon we get that mound-shaped symmetric kind of distribution, which is classic for the one variable sampling distribution. And now we're going to extend it to two variables. So here's an example for two variable. Notice that we have height of children, but we also have their age. So now we can plot height as a function of age, and we get this regression line. All right, the regression line has this slope, which is 8.94. What I'm going to do is kind of collect the slope just like I was collecting height in the one variable example. And so here, right, is the one slope of 8.94 approximately. And what I can do is then collect a different sample. This is 20 children, their ages and their heights. So if we do 20 different children, well, we get a different regression. And you can see here's this other slope. And if we keep getting different groups of 20 children, of course, just like the one variable example, right, we're going to start collecting a lot of slopes for different regression lines. There's not one regression line now. This is the sample regression line, right, and that is going to be different for each sample. Here we can do 10 at a time, and maybe let's go 100 at a time again. Takes a little bit longer. And you can see that we still get this mound-shaped symmetric distribution for the slopes when we're talking about two variables. What we need to do now is figure out some notation. So we can talk about the true regression equation, which uses some Greek letters, alpha and beta. All right, and then we also have our sample regression, which is a little bit more familiar. We have our y hat, our a, and our b. Although, again, on the AP exam, right, they use b naught and b1, but it's the same thing, just different symbols. So inference can be made actually for any of those three parameters, both the y-intercept, the slope, and the standard deviation. But really what we are going to focus on is just the slope. That's the most typical both confidence interval and test of significance that we will do. So let's talk about an example. So what we're going to do is construct a 90% confidence interval for the slope of the regression line that describes height as a function of age. Here's our data of height and age. And there's our scatter plot. You'll notice that 9.41 is our sample slope, centimeters per year of growth. But really what we want is what's the true regression slope? What's the true amount of height per year that we can expect from children? This, of course, means inference. And for inference, we, of course, have to meet conditions for inference. These are a little bit different for two variable, although you'll see are similar in many ways. There are 5 conditions which conveniently have an acronym liner. L stands for linear, which means the scatter plot of your sample data should show an overall linear pattern, and if you look at the residual plot, there should be no pattern there, which again is confirming that there's a linear relationship between x and y. I is independent, right? This should be our 10% rule if we're sampling without replacement. And of course, we also need to look at any other issues that might intervene in establishing independence, such as time series data, things that, this time depends on what happened previously, which would be not independent. N is normal. Now, what do we mean by normal in two variable? Well, you can see this nice diagram here that for any particular x, the y's would vary normally about that one x. And here's a different x, and as we take different samples, we would expect to get different y values, and those y values would vary normally. Now, we don't usually have enough data to really look at all the variations about each individual x. So what we usually do is just look at the residual plot and say, well, if it's random and rectangular, that would suggest that it would be normally distributed. E stands for equal standard deviation. And again, what we do is look at the residuals. So the residual plot is very important for these conditions of inference for two variable. And if it's roughly the same about the zero line of the residual plot, and we'll go through this particular example of age and height, and I'll show you what I mean when we look at the example. And then R is, of course, random. The data should come from a well-designed random sample or randomized experiment. So let's go through this particular example of age and height. So here is, again, the scatter plot. I've made the residual plot down here. Right, and L, yeah, it looks like the scatter plot does show a clear linear pattern, and the residual plot doesn't show any other patterns. So linear is probably the best fit for this data. It is reasonable to say that there are more than 200 children. This is a sample of 20, n is 20. So 10n would be 200. And so it's pretty reasonable to say that there's more than 200 children in the world, or at least even in this region that we're talking about. Normal, all right, so the residual plot is approximately random and rectangular. Oops, looks like I spelled rectangular wrong. Oh well. But that still confirms. Now E, here is the zero line, right? So not only is it random or rectangular, but the amount above the zero line and the spread below the zero line seems to be approximately equal, which would suggest equal standard deviations. So that is confirmed. R is that well-designed randomization. The sampling methods were unknown, so this is a proceed with caution. Inference is only possible when well-designed randomization is used. So that is a proceed with caution. It doesn't exactly confirm, but it doesn't deny either. So really, our conditions for inference have been met, which means we can move forward. Right? And just like we did with one variable confidence intervals, we need the distribution, sampling distribution. In this case, it's the distribution of sample slopes. And so the center should be our sample, just like in one variable, 9.41, that's the same. Spread, on the other hand, this is where it's a little bit more complicated than one variable. If you look at the textbook, the equation for the spread for the sampling slopes, or sample slopes, is this. This, of course, would be the ideal if we knew the population parameters, at which point this would be a normal distribution. This almost never happens. If we knew the population parameters, then we wouldn't have to do inference for beta, which is the population slope. So that really never happens. So what we have is just one sample, right? Sample statistics, which looks like this. We'll go over what that means, all the pieces. And what that also means is for the distribution, it's always going to be a t-distribution. So we have one sample to get the spread, we use this equation. For the distribution, it's going to be a t-distribution. So now, how am I going to remember this weird equation? Well, let's remember the one variable equation for just a one sample t-test, right? Which was a fairly simple equation, which was just sample standard deviation over the square root of n. Right? Notice that what we're doing now is talking about two variable, right? And in particular slope, which is rise over run. Rise, of course, is y's, run is x's. So when we look at this standard error equation for slopes, right, standard error for b, which is slopes, then really this top s is our spread for the y's. That's a little bit more complicated, which I'll get into in a moment. And the sx is the spread for the x's, so it makes sense. We have rise over run, y's over x's. And if you'll notice, this is square root of n. We've increased from one variable to two variable. So kind of the rule of thumb is that generally that decreases the amount of degrees of freedom by one. So usually, we'll see n minus 1. Sometimes we'll see n minus 2, depending on what the base equation was. We kind of reduced by 1. So now let's work through the parts. The easiest one is this spread of x's. Right? That literally is just, we use 2 var stats. Our x's are age. So you could do 1 var stats of L1, and that would be fine. You do 2 var stats L1, L2. You get the same number for the spread of the x's, a sample standard deviation for x. Now, this one, I've kind of been saying spread of y's. That's not exactly the same as what we just did for x's. Really, what we're doing is it's the spread of the residuals, right? Because when we take the sample standard deviation for the x's, that's, the deviation is x, the distance from the x measurement from the mean. Well, for residuals, it's the distance of the y, not from y bar, but from the predicted y, or the equation, the regression equation. So really, this is the spread of the residuals, right? Which we can get, first of all, we're going to need our regression line, which is in the calculator will be y1. I store it in y1. I've used y hat here, but in the calculator it'll be y1. It gets my regression equation. All right, now I'm going to need, again, a little space. I'm going to use L3 to actually calculate these squared residuals. The equation for that, right, is going to be L2, which is our y, minus our prediction, which is our equation with the x substituted in. So that's our y hat squared. And if I do that, I get my squared residuals. And once I have those, I can add them up, which is this big summation sign. At which point in time, I can really just plug in the numbers. Again, n is 20 in this case. You'll notice the n minus 2, like I mentioned before, because it's 2 variable. And it turns out that we have 12.5. Be careful about making a common mistake. Students in the past, it's a lot of work to get this. You get your 12.5 and you say, that's my standard error for this distribution. No, it's not. That's just the numerator for the standard error equation, which we can plug in both the 12.5, 1.667, our n is 20, and that turns out to be 1.72. That is our spread. And once we have that, then we can actually dimension out this distribution by adding 1.72 above the center and subtracting 1.72 below the center. So now we have our distribution. We can actually do the confidence interval, which in this particular case is 90% confidence interval. So we need our t statistic. We use inverse t in the calculator. We're using 0.95 because, of course, it's going to be the area to the left. So we have 90% plus the tail of 5%. because if it's 90 in the middle, it's 5 on both sides. All right. Confidence interval, or the inverse t, the degree of freedom is 18, because again, with two variable, degree of freedom is n minus 2, not n minus 1 like it is for one variable. And we get 1.73, which means we have, almost 1 3/4 standard deviations above, 1 3/4 standard deviations below, which means we can calculate our lower and our upper bounds, which gets us our confidence interval with 90% confidence, and we're done. Now, definitely a lot of steps in that. The next thing I want to do is show you how to do all of that on the TI-84, oops, not that, the TI-84 calculator. So I've already plugged in my data into L1 and L2. If I go to stat and I go over to tests, if I go down a ways near the bottom, we have down here two linregs, F and G. We have linreg t-test and we have linreg t-int, right? That, of course, is the t-interval, which is exactly what we just did. So I would select that. I have plugged in my x into L1, my y's into L2. All right. Frequency is the number 1. We don't have any additional frequencies. Confidence level, I should probably change that to 90. 90% confidence. I can store the regression equation. I don't have to. I've actually already run it, so it's already been stored. But you don't have to. And now all I have to do is hit calculate. And you'll notice here's the interval 6.44. Right? Here's my 6.4 up to 12.41, 12.4. So it's confirming nicely. Right? You can kind of go through. Right? There's my sample slope. There's my degree of freedom. It gives you some other statistics, the R and R squared. That's kind of nice. But really, it's up here. This is the confidence interval that you can use your calculator for.